Hello, everyone, and welcome to today's webinar titled Protecting Your Emergency Generator Set, Relays, and Coordination. I am your moderator, Lou Signorelli from Caterpillar's Electric Power Division. To those that are returning participants, we thank you for your support. And for those new folks joining us for the first time, we hope to see you every quarter for these educational sessions. Today's topic is Protecting Your Emergency Generator Set, Relays, and Coordination. As a means of a bit of level setting, I'd like to provide just a little bit of background. Electrical systems commonly use fuses and circuit breakers to protect their electrical equipment. A circuit breaker coordination study is used to analyze the tripping times for the series of overcurrent devices being compared. Generally, that means from the source through the largest branch circuit device. Coordination studies, or in some parts of the world called protection and selectivity analyses, are done to determine proper coordination of overcurrent protection devices. Lack of coordination between overcurrent devices can result in upstream devices opening and needlessly interrupting power in other parts of the electrical distribution system. Lots of great professionals here today. Consulting engineers lead the pack at 64.9%. Thank you, everybody, though. We appreciate everybody's participation. At this time, I'd like to introduce our featured presenter for today, Brian Snyder. Brian has 18 years of experience with Caterpillar, ranging from generator engineering to complete systems integration. With Caterpillar's engineering teams, Brian has supported generator and genset control products, along with leading the engineering of Caterpillar's UPS product line. Brian also led projects as a project manager related to the design and execution of customer emergency power systems. In Brian's current role, he provides application support to dealers and customers looking to develop integrated electric power systems. Brian holds a Bachelor of Science degree from Purdue University, as well as a project management professional certification from the Project Management Institute. Brian, thank you much for presenting to our group today.
Thanks, Lou, and thanks everybody for your attention today. Today we're going to be discussing the protections which are available within an emergency power system and how best to coordinate the multiple levels of protection to achieve the best operational results. This webinar is intended to be the basics of a coordination study. This is a complex subject that we're going to attempt to simplify so you can recognize the importance and coordination of all the protectives within the system. As we discussed today, we're going to start off with an overview of a single line diagram and a graph that we'll be using throughout the presentation. We'll then look at reviewing the different protective devices that we may find within the system. And then we'll look at defining system coordination study and how its impact is on the generator set investment. We'll look at the settings within the relay curves, and then we'll look at our circuit breaker options that we'll have along with coordination of those circuit breakers. And finally, we'll wrap up with some analysis tools and software, along with some additional information and resources that are available to you. So as we start our discussion, again, we're going to look at a single line that we're going to be using throughout the presentation. We've simplified the single line down to remove any references to the utility, an automatic transfer switch, or any of the transformers potentially in the system. What we're really looking at is the coordination of and protections associated with our generator set and the overall systems connection. So the one line starts at the bottom with the generator set. Inside the red bounding box is what we would consider on package within the generator. The circle at the bottom represents our generator set itself. And then up from that is a protective relay that we'll discuss here in just a couple more slides. As we move further up, we have the circuit breaker inside the square, which is our on-package circuit breaker. So this is our overall and generator set together. As we move up the drawing, we see that there are 3 different loads. Each has multiple different circuit breakers protecting those different paths of power. And each of those different zones in between the circuit breakers is what we're going to consider as our protection zones. So we're going to be talking about how we manage those protective zones and making sure that we're managing the overall system. Throughout the discussion, we'll talk several times about faults within the system, and we're referencing that in this regard as a short circuit. If be indicated by an X to show you where in the system we're talking about the fault occurring. so that we can give an overview and understanding of how that system should perform dependent on where the fault occurs within the system. The other piece that we'll be using throughout the presentation is a graph so that we can graph the different protective settings that we have associated with this. So the graph we'll use is a time over current graph. We have time in seconds on the vertical axis or the y-axis. We have the current and a per unit rating across the x-axis. The 1 will signify 100% or the full rated current of the generator that we're working with. So the next thing that we're going to talk about is the relays within the system and what relay protectives we may have within a typical generator set system. An ANSI IEEE device numbers are typically what we see within the system. These are a list of things that we would see with a generator set. The list here has the ANSI IEEE device number associated with it. If you'd like a complete list of the different devices that are available, you can see the IEEE C37.2 standard for electric power system device function numbers, acronyms, and contact designations. So as we talk about the different devices that we have within a system, what we're looking at and considering is to be able to detect a fault wherever it occurs in the system. And a fault may be any different type of anomaly as we're doing our protection. As we talked about at the beginning, we're going to be mostly talking about short circuit faults within our discussion today. But depending on where the protective relay is within the system, we may be looking at inside the generator, which we would consider anything that comes up to the generator circuit breaker would be something that we consider inside the generator. And then, or we could be, depending on if the relay is located in other portions, we may be looking at faults that are occurring outside the generator or anything that's beyond the generator circuit breaker. There's also going to be multiple levels of protection within our system. We're going to have specialized controls such as the generator set control panel, the voltage regulator, or the circuit breaker. There's also complex controls that you'll find within your switchgear or within a single or multifunction relay, depending on how your application is designed. For our discussion today, we're going to focus, as we talked about, primarily on the generator's protection. So we're going to look at the protectives associated with our generator set control panel and with the circuit breaker. So these are going to be the 50 instantaneous overcurrent, the 51 AC time overcurrent, and the 52 AC circuit breaker. And you'll see those designations by their device number in the drawing as we go forward. Wanted to note at this point also that there are several of these protectives that you'll find within your control panels potentially on package. The ones highlighted in bold are ones that we typically carry on our Caterpillar controls. The ones that are not in bold would be something that would be part of your Caterpillar switchgear. Typically that's going to be more of a system level view or something that's going to be a little bit higher level. So you can work with your CAT dealer to get spec sheets on the different products that we have and the different capabilities and what we have available to you in those different options. There's also different settings within all of these different protectives that allow you to adjust them to be able to specialize for your specific application. So let's talk about what a coordination study is. The IEEE Standard 242, Recommended Practice for Protection and Coordination of Industrial and Commercial Power Systems, is really the overarching document that gives good instruction on what a coordination study is, how to perform a coordination study, and what are the different things and considerations you might have with things such as your transformers or fuses or other parts of the system. So I highly recommend that as a more complete document than what we're going to cover today. Overall, the IEEE standard discusses a coordination is the selection and or setting of protective devices in order to isolate only the portion of the system where an abnormality occurs. The standard also goes on to talk about that a coordination with downstream circuit breakers is required for the generator to clear faults. And what this is talking about is that as we'll talk through the discussion today, we'll show the requirement to be able to make sure that the generator itself, as the source, is able to create enough energy or current to reach the downstream loads and to clear the breakers downstream. And so we'll talk about that as we look forward into the discussion as well. And finally, it also references that a sequential fault clearing closest to the fault protects equipment and provides system stability. So what this is referencing is that if we were to have a fault somewhat on load 1, like we show here, we want to clear the breaker, the 52 device, that is right in front of that fault. So there's a specific protective zone that we want to be able to have, and that's the zone that we want the 52 device to be able to protect. So in this case, we would drop the power to load 1, but we would still be powering loads 2 and load 3. Now, if the fault was to move up the system a little bit higher into the next protective zone, we would see that the fault now occurs. We want to be able to clear the next level up 52. So now we would drop the loads to 1 and 2, and we would continue to power load 3 in this instance. And if the fault was to occur directly outside the generator, we would need to trip the generator circuit breaker. This would drop the load to drop power to all the loads. But overall, now we're protecting the generator and the asset and the investment that we have made. And finally, we have the overcurrent protection device. Now, the overcurrent protection device, as we're showing here, is a 51. That's the AC time overcurrent. And what we're looking at here is the ability to identify a fault that has now occurred potentially inside the generator or inside that generator set circuit breaker. So we can now send a signal to the generator to turn it off and to stop producing current. And so now we can protect, again, our generator asset. This also works if for some reason one of those breakers that we talked about in the system failed to open. We would still have that 51 device as a secondary level of protection that's protecting our asset overall.
And it looks like, by and large, there's going to be some kind of coordination study required. Clearly over 60% of the time. So that's really good insight. Thank you, everybody, for helping us understand how and when these are used. So Brian, if you would continue, please.
Thanks. So as we said just before the poll question, one of the biggest things that we're looking at is trying to protect that generator set investment. So along with the entire system and making sure that the system stays up, we're looking at our generator set as a large asset within our standby power system, and we want to make sure that we get the most out of that investment. So one of the things that we're looking at is that as current flows through a wire, it generates heat. And over time, that heat will degrade the insulation within our generator sets. So what we are going to try and look at is that each different generator may have different classifications of insulation material, and that different classification will have different life expectancy based off of different temperature ranges. So we have a white paper that we'll reference later that the temperature rise and insulation class relationship that walks through the differences that you'll see based on temperature and based on those different class of insulation. But you also see that in the same classification of insulation, that as you increase the temperature by 10 degrees Celsius, you're going to actually reduce the life of that generator insulation by half. So in this example that we're showing here, a generator with 180 degree C operating temperature would be expected to have, with a Class H insulation, which Caterpillar uses Class H insulation on almost every generator we sell, it's going to be about a 20,000 hour life expectancy for that insulation material. So what that would be is a typical application for a standby generator set. Now, if the generator is operating for prolonged periods of time with an overcurrent or above the typical rating, it's going to see an increase in temperature, and you're at 10 degrees Celsius of an increase. As we said, you're going to half that life. So now you're getting around 10,000 hours of life instead of the 20,000 that was expected. And that degradation isn't an instantaneous failure, but eventually you get to a point where you cause weaknesses within the system, and it could potentially cause a failure that could cause the entire generator to have a short and end up being a catastrophic failure. So we want to make sure that we're protecting that asset and that we're getting the most life out of the investment that we've made. So let's talk about those relays a little bit. The generator set relay that we discussed before, the 51 AC time over current, has multiple settings within it that we're going to need to make a decision on how we set up that relay. The first set point is the definite time setting. This is, as it states, is you set a current setting and a current threshold. So typically you have between 100 to 300% current that it will allow. And then you set a time delay. So in this instance, we have 1/10 of a second up to 20 seconds. And so once we've set those time settings, when the current hits that threshold, the generator will receive a signal to stop producing current. So as we've shown here in the graph, we have a purple line representing that 100% for 1/10 of a second. And then the gray section is really showing all the potential variation that you could make those settings to. Now, setting it to 100% for 1/10 of a second is probably not likely in most applications because as soon as you hit that full rated current of the unit, within 1/10 of a second, you're going to get a signal that's going to tell you that you need to shut the generator off. And that's not necessarily what you would want. So a more common setting that you may see is setting the unit to 300% for 1 second. Now, our Caterpillar generators, typically at 60 hertz, are rated for 300% for 1 second. For a 50 hertz product, that may, or sorry, 300% for 10 seconds. A 50 hertz product would typically be around 250% for 10 seconds. But you can work with the dealer, your CAT dealer, to understand what your specific unit's capabilities are. So in this application, we've set the units to 300% again for 1 second. So now, if we were to have a fault within the system, that would be something greater than 300%. So in this case, we're showing 10 times the rated current. Again, with most generators, you're going to need to work with your manufacturer to understand if 10 times the rated current is available from your generator. That's going to depend on the current decrement curve that you're able to get from your manufacturer. That will also depend on whether or not you're using a permanent magnet excitation system or a self-excited, or whether or not you've got enough subtransient reactance within the generator to actually provide a large amount of current. So those numbers will determine whether or not you can get to 10%, but for this example, we're going to say that we can. And then at 1 second, the generator would trip offline, and that would be our trigger. So now if we also, though, would see that if we were to have a fault within the system and the fault required just 200% current, and so we did not have a 300% over current, then we would end up providing that 200% on a continuous basis because the definite time trigger isn't able to actually identify that there was a failure because we set the time or the current limit to 300%. So because of this, we don't only just use the definite time settings. It is our first setting, but not the only one we use. There are also curves that are available within the relay set points. So the curves are based off the IEC 60255 standard. You can see the formula here that's used to calculate the curve along with the values that are used. These curves are programmable. You can use a current threshold of 100 to 300%, and that allows us to move that curve horizontally across the axis, or we have a time multiplier that allows us to also move it slightly vertically. The overall aspect of this now is that what it does by having a curve is it gives us the ability to have a little bit more room and a little bit more power within that area left of the definite time curve setting. So it's the time rated. We can have longer time trips and be able to provide, in this instance, we're showing the 200% fault again, and the fault occurs and is tripped off at 5 seconds rather than providing it continuously. Now, there's also value to the curve on the right side of the definite time or within that short time range. Typically, though, the generators in this case were showing that you would require 100% or 100 times the rated current of the unit, and it's very unlikely that a generator is going to be able to produce 100 times the rated current. But in this case, if it was, you would trip off slightly faster than what that definite time setting would be. So there's not only one curve available to you. There typically is the normal inverse curve, which we see as the blue curve on the graph. We also have the very inverse curve, which would be the red curve that starts giving us slightly more current to the left side and slightly less on the short time range. Or the extremely inverse, which provides even more current available or more time available to the left side of the curve, and it provides us less current capability on the short time range of the curve. So what this would do is, by making the selection of which curve you want to use, you are determining how long you want to be able to provide that current during the overcurrent on the left side of that curve. We're seeing that if we were to go with the normal inverse, we would end up with the roughly 5 seconds that we discussed earlier for that 200% overcurrent. If we were to use the extremely inverse in this situation, we would end up with 10 seconds of overcurrent during this application. So by choosing which curve we want and how we set those settings within the curves, it determines how much current we're going to see and for what duration we will see that current. There is one additional curve that's available in most generator sets or in Caterpillar's generator sets. There is the thermal limit protection curve. The thermal limit protection curve does not have a time multiplier. It only has a current multiplier. And this curve is intended to follow what would be the rating of the insulation class material that you have. So in this case, we would see that we can now get more time on the short or in the long-term settings over to the left of the curve, and we can use the current multiplier to now move that across the x-axis. The reason why you would have the current would be because of the ability to have an oversize, or that you would need to want to reduce down that a little bit so that you're not taking into account more current than is necessary. So as you can see here with this curve, we've now overlaid the generator thermal limit as part of the overall curve. So we have the thermal limit protection curve, where we can see that we're getting, instead of that 10 seconds that we had previously, we are now getting up to almost 30 seconds of additional energy. And the generator thermal limit, that we can see that we are right on top of that thermal limit. So now we know that we're going to be up to what the capability of the unit is, and we're getting more energy that we need to be able to support those downstream loads or to clear these faults that we have within the system. It'll aid as we go forward and talk about how we coordinate this with all the other breakers in the system at the end.
Now let's go to our results for that poll question. Looks like the engineer of record has the predominance, or maybe perhaps the electrical contractors in combination, from a scope of supply perspective. Thank you, everyone, for sharing your insights from your experience. We appreciate it. Brian, how about we continue?
All right, thanks. So we've talked about the protective relays and the protection that we have associated there. Now let's start looking at our circuit breakers in our system. There's primarily 3 different types of circuit breakers that we're going to talk about. There's a molded case circuit breakers, there are insulated case circuit breakers, and there are power circuit breakers. So the first breaker we're looking at is the molded case breaker. This typically has a low to high interrupt ratings. So these are breakers that you may find, like I talked about in the beginning, in your home, all the way up to something that would be throughout your system. Typically, these are going to be the breakers you find closest to the loads overall. They are typically a low short time rating. They're mechanically operated only. They also are available typically only in a fixed configuration, and they're going to be typically an 80% rated breaker. Almost always they're a factory sealed application, which means that the breakers are not serviceable themselves in the field. So if you have a failure of the breaker, you're going to have to take it out entirely and replace it entirely. And they have the least rigorous test standards overall for the different breakers that we've discussed here. So the next breaker is the insulated class case circuit breaker. The insulated case breakers typically have a higher interrupt rating. They have a medium to short time, a medium short time rating. These are normally what you're going to find more in the distribution part of the system. They use a stored energy mechanism, either a mechanically operated or an electrically operated mechanism for being able to open and close. They're available in a fixed or a draw-out configuration. They are typically 100% rated, and they have limited maintenance capability. So there's a few things that you're going to be able to change, but not necessarily everything. And then they also are the same testing standards that you're going to find with those molded case breakers that we talked about. And the last breaker is the power breaker. The power breaker is normally a high interrupt rating, so it's typically going to be at the distribution level within the facility. It's also a high short time rating. They're capable of fast reclosures, and they're available in both fixed and draw-out configurations. These breakers are almost always 100% thermal rating, and they're a highly maintainable breaker, meaning that almost all the parts are something that you can take off in the field and you're able to do the maintenance in the field versus having to remove the entire breaker and ship it back. So with the breakers themselves, the breaker is the physical device that's doing the opening and closing of the path of power. But the breaker itself then has a trip unit that will be part of the breaker that will be doing the monitoring and will really be making the decisions on when to open or close the breaker. There are different types of trip units available. Typically, there's the LS, which is a long and a short time trip. There's the LSI, which is a long, short, and instantaneous trip. And there's the LSIG, which is a long, short, instantaneous, and a ground fault trip. You want to set those trip settings, as we talked about just a minute ago, more focused on the load. So you're going to make the decisions on what settings to use based on the load that's connected to it. But you also want to be below the control protection relays and below those generator thermal curves. So as we talked about earlier, we'll be looking here as we go forward at coordinating these, and we want to make sure that we're sort of to what we would consider the left on the graph as we continue to move down the path, even though we're providing enough energy for the load, but we're also protecting the system. The settings and the different information that's available should be available to you from your manufacturer. Caterpillar has spec sheets that you can work with your Cat dealer on all the breakers that we provide so that you can get the data that you need for these coordination studies based on the specification sheets so that you can understand what are the requirements and how to size the breaker and how to set the breaker within your system. So let's look at some of those settings that we might have. With the circuit breaker, the first section that we're going to look at is the long-term, long-time or thermal trip settings. Typically, it's considered thermal because there's a bimetal that's used, and it uses temperature over time to be able to be the determination for the setting. But we're able to make those settings with both a current and a time threshold, so we can move that curve at the top portion, left or right or vertically, to be able to set and align with the settings that we'll show as we go forward within the system. So in this application, now we're showing that potentially we would be able to provide just over the fully rated current for just over 100 seconds in the way that the system is designed. So the next part of this curve is the short time or the magnetic portion of the pickup. This again has a current and a time threshold that we can set. This looks a lot more like that definite time setting that we talked about before. So we're basically setting this, instead of having more of a curve, it's more of a corner function. And so we set the amount of current that we expect to see, and we have a time setting, and it's going to basically, once we hit the current at that time, it will open the breaker. And the last portion is the instantaneous trip. And so the instantaneous trip is really where we're going to try and set the unit so that we know that we're going to trip off as soon as we receive or identify that the current has reached that point. That's going to be an instantaneous trip. There's typically only a current threshold for this because of the fact that, as it states, it's going to react as soon as it can identify the current and open. Now, something else you'll notice different about the breakers rather than the relay settings is that there's a shaded line thickness here. The thickness that we're seeing in the line here actually represents the full period of the actuation of the breaker. This is the identifying of the fault that's occurring. This is the physical opening of the breaker and extinguishing the fault within the system and the current that's flowing through it. This also takes into account the variability in manufacturing of breakers, and that not all breakers are exactly the same or manufactured exactly the same. So there's going to be a little bit of variability overall for the different breakers. And so you take that into account with this shaded region. The importance to understand here is that we don't want to overlap those shaded regions necessarily as we're looking at our different protective zones, because if we were to overlap the different shaded regions, we could end up getting to a point where we tripped one breaker out of turn because of the fact that one operated faster than the other one did on that specific application. Even though we thought that one should have started operating faster, maybe the other one was able to respond quicker to the fault. So we want to try and make sure that we're not overlapping those regions overall. So now we're starting to look at this coordination function and how do we coordinate these different breakers within a system. So as you can see, we've now brought that relay protective and the generator breaker all together on the same graph. And now what we're looking at is, as we see up into the long time settings, we're able to follow the curve as much as possible. This allows us to give as much current as we need from the generator and as much as we're capable of providing without tripping the generator breaker. And then as we look down more into the short time settings, we now have that difference between the definite time setting of the relay and the short time of the breaker. And that's the section that we're going to adjust the time setting, and we'd adjust that time interval to be our coordination overall. If we don't necessarily need to be able to provide that, say, 200 or 300%, depending on how that setting is, for more than a 0.2 of a second, then we'll set the breaker at that 0.2 of a second and allow the protective relay really to be the backup to the breaker. But overall, this is our coordination and making sure that we're aligning these different pieces to allow enough current to support the loads, but that we're protecting the fault. So as we see here, if the fault is occurring just directly outside of the generator breaker, and in this case, we're roughly 300% of the rated current, then we are going to be tripping the breaker at roughly 0.2 of a second versus the full second that we had set for the protective relay. So Lou, I think we're up with another poll question at this point.
Absolutely, and this is where it starts to get fun. So everybody thinking caps on. If a genset controller was to function as a protective relay, would you consider removing the on-package genset circuit breaker, assuming, of course, that it meets local codes, etc.? The answers are simple: yes, no, I need more information, or other. If you would please share your experience and thoughts on that one. Hey, Brian, while they're working on that, this is very interesting to me. Would certifying organizations like UL allow an on-package breaker to be removed from the generator set?
So actually they do, if the generator set had been tested and verified to meet their design requirements without the breaker. So for an example, Caterpillar can provide a UL 2200 rated package without a generator mounted circuit breaker, because we have shown that the protective settings that we have with our overcurrent protection provides the same functions and are able to shut the unit down. So that is possible to be ordered based off the customer's request. It would be recommended that you work with your local dealer on those discussions because you are going to want to have a physical disconnect somewhere close to the generator for maintenance and to be able to remove it from the system. So you want to make sure that you coordinate that, and some codes will have a specific distance that they require that physical disconnect. But from a UL standpoint or a certifying body standpoint, it's often that we can get approvals to be able to ship packages without a package mounted breaker.
Brian, thanks for that. And just a little bit of color to that. When we talk about physical isolation, that could be as simple as a manually operated breaker that you open and close for maintenance or what have you. Is that correct?
Correct. You don't necessarily need the whole trip functionality that we've been talking about with trip relays. It's really looking at a physical switch within the system. There's varying different levels that you can get to with that, but it's one way that you can manage reducing the overall number of things that we're trying to coordinate within these systems at times.
And I'd imagine that breaker is a lot cheaper than what we're talking about with full-blown trip units, et cetera.
Potentially, yes.
Yeah, great. Okay, terrific. Well, let's see what everybody had to say about this one. 62% would not consider it. 20% said that they need more information. That's good to hear. And 15% said yes, they would absolutely remove that cost from their overall system. Terrific. Well, Brian, let's keep going. Thank you very much.
Thanks, Lou. So we've worked ourselves outside the generator now. We've completed the relay protectives. We have the generator set protectives, our circuit breaker, and now we're starting to look at the breakers throughout the system. So as we move again more to the left of the curve, we want to continue to add more breakers, more consideration for our loads. So as we think about this now, the breakers are probably going to be something less than 100% of the package at a continuous demand because you're not going to have two loads within a system that are going to both be 100% of the demand of the system. So this one, in this case, the blue curve is now representing a breaker that's a feeder breaker down into the system, feeding our load 1 in this instance, which would say roughly about 20% of the rated would be supported continuously. And then we have a curve that's allowing some additional power for different reasons. So in this case, if we were to experience a fault that is just under the 100% rated for the package, we would actually clear the fault at around roughly 5 seconds, and that would be the breaker further, the 52 device shown further down into the system. If we had that same amount of power and for some reason that breaker or that 52 device did not trip, then we would go all the way up to just over 100 seconds before the generator breaker would recognize that fault and see that as a failure and trip the system. So we want to make sure we're coordinating to, again, allow enough current to the system to support loads as necessary, but we're also coordinating these breakers such that we're protecting the system overall. And in the end, we will continue as we move, again, more breakers into the system. We will continue to add more to the left of the curve. In this instance, again, we're looking at the system and saying, if we have a fault that occurred at where we show location 2 here, and we still have that same discussion before, we would trip the breaker that's feeding both loads 1 and 2, but we would still be able to support load 3 within the system. So we're doing that selective coordination where we have the different protective zones are all being considered. We look all the way down into the loads, and we're making sure that we're protecting each level as we go down towards the system. So in a coordination study, and when you really are starting to do this with a full system, there's a lot of data to be gathered. You need to gather the information on your circuit breakers and the different settings that you have available to you, the long, the short, and the instantaneous trips. you need to look at your different protective relays that you may have within the system and making sure that you're taking those into consideration so that you're allowing enough current when necessary. You also have to look at your sources and say, what is our current decrement curve? What's the generator thermal damage curves? We want to make sure that we're taking all those into consideration so that, again, we know that we're providing enough current when necessary and that we're still protecting our assets. You will also, typically, you'll look at the transformers in your systems, and you may have transformer damage curves that you need to apply, or the cables even, because as we look at our protective zones, cables have insulation life, and we want to make sure that we're putting into account that thought when we look between our different protective zones so that we're protecting the cable as much as we're protecting the entire system. So this can become a very complicated process. And there's a specialized software that is available that you can use to do these coordination studies. They help to look over all this information and help you to make decisions based off of what set points you want to be making. Make sure you're coordinating those breakers so you're not allowing too much time between one breaker and the next, but you're still focused on supporting the loads and protecting your overall assets. So Lou, I think we have one more poll question. So it looks like the poll question is, if you've used a tool to help with the coordination study or the protective and selective analysis, what tool did you use most often? We have ETAP, SKM, EasyPower, and other.
Brian, thanks for reading that. So everybody, if you'll share your personal experiences, whether it's a tool that you're familiar with, that you use or know that someone uses, help us understand who's using what in the marketplace today. So Brian, forgive me, but it seems like an awful lot of data to complete these coordination studies. How do I go about getting all this information?
So most of the information should be available from the manufacturers. And honestly, it's really good to start getting involved with your manufacturers early on in the design process because they can help you to understand what different options they have available to you, what are the different set points. For example, a lot of times customers may not recognize all the capabilities that are within the generator set control panel, and they end up purchasing additional protectives that they'll add into the system that end up creating overlapping protections that need more coordination, more calculations, and we end up, one, it's double the investment that you're putting in, but sometimes it even makes more complicated the coordination of the entire site. So it really is good to work with your manufacturers as early on in the design process as possible to make sure that you're making the best decisions and getting all that collected information as you go.
So it really is a best practice to kind of assemble my brain trust of partners as we start the project so that we're not trying to scramble at the end. Is that right? Right.
That's exactly right.
Got it right. Terrific. Let's see what everybody had to say. SKM at 49.5% is leading the pack, closely followed by ETAP and EasyPower. There are a few others out there even pushing up 20%. Good to know. It looks like there's a lot of tools out there for folks to use. That's really good news. So Brian, back to you.
Thanks, Phil. So when it comes to the software, Caterpillar's been working with several of those manufacturers. In all honesty, any of those that stated other, we would really appreciate if you told us what that was in the Q&A section so that maybe we can look at some of those other manufacturers as well. But we are working currently with SKM that you should see with their next release of software, that they will include our Caterpillar EMCP4 overcurrent relays. So you'll be able to take the relay set points that we currently are talking about in the presentation today for the package. This will help with a lot of those decisions that we may have where those customers are looking at and say, do we want to remove the onset or on generator pack breaker and move that off the package? You may be able to make those decisions by looking at the relay set points and doing your coordination a little tighter. Overall, there also is an overcurrent protection relay tool that Caterpillar has. You can work with your Cat dealer to model these different set points, be able to make the decisions on whether or not you want to go with the normal inverse or maybe the thermal damage curve. It does include our thermal damage curve as part of it. So you'll be able to look at what you'll see with your product and what you'll be able to get with your Cat genset. Additionally, there are other resources that are available that we would like to point out. We talked about a couple of times, there are some white papers. If you go to cat.com and search for white papers, you'll be able to find our overcurrent protection white paper. We have a white paper that we talked about on temperature rise and insulation class relationships. There's even one on our arc flash energy reduction mode, which is basically the ability to provide a setting to the generator set that will reduce down the protective settings to allow you to do more maintenance on the product and allow our maintenance teams to be able to work safely in a safe environment. This aligns with the NFPA 70E requirements that you'll see in many areas. Also, there's our SpecSizer tool. You can go to specsizer.cat.com to look up more sizing. There is more information there on also spec sheets are available from that location, and a lot of the data, if you size up your application, you'll be able to download a lot more information. Further, if you like these type of discussions, Caterpillar has also launched a podcast that's Power Bites. You can download that from wherever you like your podcast. Also, the link at the bottom is our link to our application site where you can go and get more information. There's links to SpecSizer, to these white papers, to the podcast. All of that can be gathered from that Electric Power Application Center website that you see there at the bottom of the page. And like always, and we've said it several times, contact your local Cat dealer. They can help with any of this information. They can walk you through any of the areas and get you more detail, or even work on getting our team out, and we can come out to your location, sit down with you, and work through more details from the Cat factory as well. So Lou, I think that's our presentation. Do we have a few questions maybe that we want to address?
Yes, but first I'd like to thank you, Brian, for sharing your insights and helping us understand the importance of protecting your emergency generator set and showing where we can find those great tools. For everyone, as an aside, Brian is the author of a few of those white papers, and it's very nice of him to give us some of his time today to share his insights with us. Brian, so throughout your presentation, we had several questions come in, and I just want to take a moment aside to the people that are sending us information on the Q&A on the other software packages. Thank you, thank you, thank you. We really appreciate that. Those will be investigated and passed on to the team that does that. So thank you very much. So let's jump into a question or two. Let's start with, this is an often misunderstood topic, Brian. So you talked about 80%, 100% rated breakers. Can you help us understand what that means?
Yeah, so the NEC requires that the breakers are able to provide 125% of their rated current continuously. And they define continuously as over 3 hours. So if you're rating a breaker and you're going to need to put it into an application that's going to be a continuous running of the breaker, it needs to be able to support 125% of that rating for up to the 3 hour limit. So typically when you say an 80% rated breaker, that's really a breaker that is only able to carry 80% of its rating continuously for the 3 hour duration. 100% rated breaker would be a breaker that's rated to be able to carry 100% for the 3 hours. So it will carry the 125% for the 3 hours. So now you can rate it at 100% of what it is. So that's where it's a little bit confusing, but typically an 80% rated breaker is going to be a little bit less expensive than a 100% rated breaker. But if you have an application where you know you're not going to be running at the full rating, that it's going to be something less the majority of the time, then you might want to put an 80% rated breaker in because it'll be less cost for you overall.
We did have, Rachel wrote in with a good question. Are all generator thermal limits the same?
So typically the limits are going to be based off of the insulation class of the material. So if a generator is a class F insulation, most of them are going to have the same thermal limits. If they're all class H insulations, they're potentially going to be all the same. But it's really good to work with your manufacturer because there may be some minor differences between manufacturers that may make minor changes within those curves. But if you're talking about, so with Caterpillar, again, we use class H insulation almost exclusively. Almost all of our thermal damage curves are the same because of the fact that we're using the same class of insulation across the board.
Interesting. While we're on that thermal topic, Mohammed wants to know, does CAT have a temp rise limit suggestion, and where should it be set?
So typically the temp rise is going to be based off the application. So with our insulation class and temperature rise, white paper would be really good reference to understand that. You're going to have a different temperature rise for a unit that's going to be continuous versus a unit that's going to be running in a standby application. And you want to make the decision based on how the unit's going to be operating, not necessarily on other factors. Because what it ends up doing is your temperature rise really determines the life that you expect out of your insulation. So if you were just to say, I want 105 degrees C temp rise, then you're in a standby application, you may end up with a generator that has somewhere around 100,000 hours of life. And in a standby application, that's hundreds of years potentially. So you don't necessarily need that. You're overpaying in those regards. So you want to make sure you're aligning the temp rise with the application. Also, if you were to say that you had a temp rise for class F insulation, but you're selling you're going to receive a class H insulation, those temp rise differences need to be taken into account because you want to, again, realign with what the expected life is, not necessarily the temperature number at the end of the day. And we walk through that a lot more in that paper.
Yeah, excellent, excellent. And then, as you mentioned, those papers are available on cat.com. Terrific. Here's a great question from Paul, and I think I'm reading into this question a little bit. The assumption is the genset circuit breaker is on package. So the question is, are the relays on the generator set programmed to coordinate with the circuit breaker on the generator set from the factory?
So from the factory, typically not. Our relays may be set a little bit lower than what you may see on the package. It's really recommended that's part of the commissioning and setup. You really want to look at those set points, make sure you're aligning with what the overall expectation is, and that you're coordinating that as part of the overall project. It may not necessarily ship directly from the factory with settings that are perfectly aligned or coordinated. So that's something that's recommended to be done on site.
Brian, this is somebody that was really paying attention to your charts and looking at lines and thicknesses, et cetera. They noticed that the thickness of those lines had changed. They want to understand, does that line thickness, what effect does it have on system sizing and et cetera?
So when we think about with the relays themselves are identifying when the trip is going to occur. So the relay is really an instantaneous time for the relay to identify and say we've hit the threshold. Then it's going to be what the reaction is what's going to be beyond that. So typically you're going to have say that the threshold is hit, and we're going to, from Caterpillar's perspective, that's part of our generator controls. So we're going to shut off the excitation to the system so that we now can shut down the generator very quickly. So the time band is really, we're talking about excitation, time constants, and things like that. It's very short, within hundredths of a second, versus maybe as a breaker was to look at it and you would see maybe a tenth of a second or even a little bit longer when we look at the overall curve. So you're looking instantaneous identification versus the actuation of physically opening breakers.
Great, great. Well, thank you, Brian, for not only making the presentation, but sticking around to help us work through some of these questions. We really appreciate it. And to everyone on the line who has submitted questions, thank you very much. We certainly appreciate it.